Hi there, welcome back to part 2 of the calorimetry and enthalpy video lesson. So as a quick recap, calorimetry is the measuring of the energy change of a process using water, and generally we just study objects for that. We're going to take it one step further now and apply it to chemical reactions, and we'll look at enthalpy. Right, so we'll look to define that, describe what molar enthalpy is in terms of the amount of energy per mole. Based on the type of reaction that's occurring. We'll look at the enthalpy of different systems and how it can be portrayed differently. So how we're told if something is endo or exothermic based on the reaction. And then we'll do some calculations involving enthalpies and mole ratios, and we'll represent energy changes in different forms using equations and diagrams. So let's jump right into it. An enthalpy change is the difference in total energy of the bonds and reactants during a chemical or physical process. That is the key here. So enthalpy change is specific to reactions. Whereas when we look at heat and Q, that can be general to an object. Okay? So if the enthalpy change is greater than 0, which means it's positive, energy is absorbed. Okay, so that means it's an endothermic reaction. And if the enthalpy change, delta H, is less than 0 after calculation, it's an exothermic reaction because energy is being released. And that's when it's a negative value. So it's important to keep those two in mind as we go through this here. Okay, the value of H determines if it's endo or exothermic. So we described previously that energy released by a system is absorbed by the surroundings. Because the system will be a chemical reaction, we're going to replace Q, right? We saw this in part A, okay, relating to thermal equilibrium. We're going to replace that with H, just because instead of an object now, we're looking at an actual a chemical reaction, which has products and reactants, which is what we defined H as right up here. So be sure to read that over one more time. So let's look here. If the enthalpy change, which is delta H, of a system is 30 joules, what is the heat of the surroundings? So very simple, H and Q are related to each other, right? H is always the system when it's involved because it's a chemical reaction. So if it's 30 joules equals negative Q, Q equals 30 joules. So what does that mean? Okay, very simple calculation, but it's interpreting it. So the system released energy, the system absorbed energy here because it's a positive value, and the system was the chemical reaction. So the surroundings, and that's where our mistake was. Forgot to add the negative sign in here when we isolated for Q. The surroundings lost 30 joules of energy because of an endothermic process. We don't say that the surroundings are exothermic. We always describe it in terms of the system. So the system was endothermic. I will say to an endothermic system. We don't say because they are exothermic surroundings, because that would make them the system themselves, whatever undergoes the change. So that's the first relationship. All right, it still applies. Energy released is equal to the amount of energy gained. Okay, just the amount in opposite directions. All right, before we move on to this, we'll go back here. By definition, because this is true, this over here, we can also say that delta H is equal to Q, which means it's equal to MC delta T. Okay, so this is a main component of calorimetry as well. And we should have the negative sign there. So the water can help us determine the energy change or the enthalpy change of a reaction, and then relate that back to a couple of different variables. So going back to how we can determine the amount of energy in our samples. All right, molar enthalpy, very straightforward. It's the amount of energy change per mole of substance. So joules per mole or kilojoules per mole, almost always measured in kilojoules per mole. Right? So it depends on what the type of enthalpy change is. We're going to see a couple of different formulas here. All right. It's based on the process. So enthalpy you'll see here based on the formula at the bottom. Okay. We describe enthalpy changes based on the type of reaction that's happening, whether it's something is dissolving. We call that the enthalpy of a solution. If something is condensing, condensation, it's going from a gas to a liquid. Combustion, vaporization, freezing, neutralization, and formation, they're all different types of enthalpy, or they're all types of reactions that have their enthalpy measured. So in general, how do we calculate this? Well, what we'll find is that the enthalpy is equal to the number of moles times the molar enthalpy. Right, so this is our main equation. And if, as a quick recall, the number of moles is equal to the mass divided by the molar mass, or the number of moles is equal to the concentration times the volume. Okay, so those are concepts from previous chemistry courses. Now, we don't put R there. Okay, the R is just a placeholder. The R gets replaced with the name of the type of process that's happening. Now, is it important mathematically? No. It's just a convention that we use to describe what's actually happening to the system. All right. So we'll look at an example here. The molar enthalpy of vaporization, so going from a liquid to a gas. A freon is 34.99 kilojoules per mole. If 500 grams is vaporized, what is the expected enthalpy change, delta H? So being able to determine what that is. Okay, we have two options. Delta H is equal to negative Q. That's more related to calorimetry, and if we knew a temperature change, which we don't in this case. Okay, we don't have the temperature change. On the other hand, delta H is equal to the number of moles times the enthalpy of vaporization. Okay, and we're going to, again, we replace that R just with the type of process, has no bearing on the math. So in this question here, we're told the molar enthalpy of vaporization is 34.99 kilojoules per mole. So all we need to do is determine what the moles are, and multiply those two values. So we're given the mass and the molar mass. So we'll say that moles are equal to mass divided by molar mass here, times the molar enthalpy of vaporization. All right, and what that's going to tell us is the molar enthalpy of vaporization is saying 34.99 kilojoules are absorbed, because it's positive, for every mole of freon that's vaporized. And what we're saying is, well, we don't have 1 mole, we have 500 grams. So what's the total energy change? So that's what delta H represents. Just kind of make a note of that here. Total energy change, whereas the enthalpy of vaporization is energy change per mole. Okay. So we can substitute our numbers in. We've got 500 grams, and this is going to be inaccurate because it's one significant figure. We're given the molar mass as 120 grams per mole, and then we're told that it's positive 34.99 kilojoules per mole. Okay, so we can take that up here, punch those numbers in our calculator. We'll leave a couple. Divided by 120.91 times 34.99. What we're going to get is 144.69 kilojoules. And note the sign on this. This is positive. Okay, we're going to put that in here because it's important. So in our final statement, we can say, what is the expected enthalpy change? Therefore, very inaccurate, but to one significant digit, we would say 100 kilojoules of energy are absorbed during this vaporization. Okay, and why was it absorbed? Because the value was positive. Now think about that. Vaporization is liquid to a gas. It's going to a higher energy state, which means it needs to absorb energy. So our numbers add up, right? So that's the relationship there. if we know a temperature change, we could use the law of conservation of energy, but we don't. It's not a calorimetry based problem. It's a chemical reaction, so we base it on the number of moles that are present. Now, because of this, that means stoichiometry applies. It is a mole-specific property. So if you know the coefficients, you can do a ratio of the amount of energy. And we'll get to that in a bit. So in terms of air conditioning and refrigerators, because Freon, when it vaporizes, absorbs energy, it makes things cold. So there's a whole process where as it passes through the pipes in the house, it vaporizes, absorbing energy, and that's what makes it cold. And then when it gets outside, it releases this. It turns from a gas back into a liquid, right? And that's why the top of the air conditioner unit appears to be hot. Okay, so that's the basic process of how it works and keeps our houses and cars cool, and our food year round. So we're going to do another example here. Okay, in a calorimetry experiment, okay, we've got all of the information here. And we're asked, what is the molar enthalpy of solution of the potassium chloride? So whenever we see a calorimetry experiment, we have to remember that Q equals mc delta T, all right? And anytime there's water involved, we know that water-specific heat capacity is a constant and that the volume is related to the mass. So let's start off with the question itself. What is the molar enthalpy of solution? So we defined molar enthalpy, and because we're using solution, we replace that with this down here. So we'll isolate for it. So delta H solution is equal to delta H divided by N. All right. So lots of ways we can approach this, but in the end, we want to know when potassium chloride dissolves in water, all right, what is the enthalpy change? So given this here, all right, because we're talking about potassium chloride, this is going to be the moles of potassium chloride and the enthalpy change of potassium chloride. So for the number of moles, we'll do this in kind of steps here. We know that it's equal to the mass divided by the molar mass. We defined that previously. Now for the top here, because it's a calorimetry experiment, we know that delta H of the potassium chloride is equal to negative Q of the surroundings. Now just as a recall, in that calorimeter, as the potassium chloride dissolves, what are the surroundings? Well, hopefully you paused and thought to yourself and you say, yeah, it's water, because that's what it's being dissolved in. So it's going to be equal to the negative Q value of the water, which is equal to negative mc delta T, and all of those values are for water. So by solving those independently, right, and kind of working our way backwards, we can determine the enthalpy of the solution. So that's how we relate temperature change back to energy change of a reaction when it's done in a calorimeter with water. Okay, so we can solve these independently, or we can combine them into one and say delta H solution is equal to negative mc delta T, and that's all of water, divided by the mass, divided by the molar mass of potassium chloride. So solve this however you'd like, right? You can do it as two separate calculations and then bring them together, right? I'm going to focus on just substituting these in. So what I would do is solve that first, and then bring them together to find your final value. So we'll say this now. So before we solve this, make sure you pause it and try it for yourself. Okay, all of the information is in the question here that we need. So if you did pause it, right, the mass, again, of everything in the numerator is water because we applied that negative symbol. Why does it work? Well, it's going to be the opposite of the potassium chloride. So whatever the potassium chloride does, it's the same amount, but opposite for water. So we had 100 milliliters, which means we have 100 grams of water. Heat capacity is a constant value we learned before, right? And the temperature change, okay, it went to 20 degrees. So if we zoom in here, 20 degrees Celsius minus 24.1 degrees Celsius as the initial temperature, all divided by the mass of potassium chloride, which was 7.46 grams, divided by its molar mass, which was given to you. MW means molecular weight, which is like the molar mass. Okay. So again, you're going to get the same value. Okay, we'll do top and bottom just separately. So 100 times 4.184 times 20 minus 24.1. And then there's that second negative sign, so those will cancel out. So we've got 1715.44, and that's in joules, okay, because of the specific heat capacity. So watch your units there. 7.46, this is going to be about 0.1 divided by, it's going to be rounded to exactly 0.1 moles. And what we're going to get as a value here, 1715.44 divided by that answer, we'll get 17,141 joules. Okay, so two ways of solving this, kind of step by step on the left, which take a value here, take a value here, and then put them together, or we can do it at once. So to write our therefore statement, okay, the question was asking what's the molar enthalpy of solution. You could say therefore the molar enthalpy of solution of potassium chloride, which just means what happens when potassium chloride dissolves in water, is 17 kilojoules. I'm going to convert that right to kilojoules from there. Okay. What does that mean? Sorry, that's per mole because it's molar enthalpy. Okay, and that's joules per mole there. Nothing canceled out for our units. So what does that mean? That means that potassium chloride absorbs energy from the water. What should happen to the temperature of the water? It should go down, which is exactly what it did. So if you dissolve potassium chloride in water, it will get colder by itself. That is a property of solutes that dissolve. So complex example review, make sure you understand the link between calorimetry and enthalpy and how the values can be used to help each other or to help interpret. All right. Enthalpy of neutralization. Because it involves an acid and a base, it's going to be written as this property here, the enthalpy of neutralization. We usually just cut off the letters at the end. Okay, so let's look at an example for this. What's the enthalpy change for this reaction? You can try A, B, and C on your own. Right? But remember, the enthalpy change is just the energy change of a chemical reaction. So it's the number with the kilojoules beside it. So we'll say delta H, not neutralization because it didn't ask for molar enthalpy, so just delta H here. Now it's on the product side, which means energy is being released, so it should have a negative value, negative 114 kilojoules, right? And that's our answer. It's not kilojoules per mole, just enthalpy change. So now if we look at this, okay, calculate the molar enthalpy of neutralization. So delta H neutralization, doesn't matter what we write here, is equal to delta H divided by the number of moles. That's our formula. So in this case, we're given delta H as negative 114 kilojoules. Found that at the top. And we can look at the coefficients for the number of moles here. So there is 1 mole of sulfuric acid, which means that is our answer, negative 114 kilojoules per mole of sulfuric acid. So in practicality, what does that mean? When we carry out this reaction, because it's releasing energy, right, it's going to make the surroundings warmer. So if we did this near water, the water temperature would increase. If we held the beaker that we did this in, the beaker would feel warm. And unfortunately, we can't do that through video. All right, now if we do this, the molar enthalpy of neutralization of sodium hydroxide, we'll do the same thing, delta H neutralization is equal to H over N. In this case, they started off with the same enthalpy, but if we look at the coefficients here, there's a 2 in front of the sodium hydroxide. So 2 moles reacted. We'll do some quick mental math. And that means 57 kilojoules per mole of sodium hydroxide are released for this neutralization. So if we look at this, sulfuric acid releases more energy when it's neutralized than sodium hydroxide per mole. Okay, even though when they react together, they release the same amount because they're part of the same system. So every substance has its own value for molar enthalpy, and a lot of times that's how we identify substances, is by reacting them and measuring their temperature changes, and then relating that back to their molar enthalpies, because there are standard values for that. Okay, so let's wrap this up just by determining how are we going to get this information. So we're going to look at the formation of water. All right, so hydrogen gas plus oxygen produces liquid water. So we'll do this in three ways. It's an exothermic process, which releases 285 kilojoules per mole of hydrogen gas. And if you look here, there's only 1 mole of hydrogen gas in this reaction. Okay, so let's take a look. Option A, we can actually find the energy in the balanced equation. So because it's an exothermic reaction, it's written on the product side. Okay, don't forget that this represents delta H. So it's just kilojoules, not kilojoules per mole. Okay? If we want to write it as kilojoules per mole, we would write energy outside of the equation. So we can do it like this, or delta H equals negative 285 kilojoules per mole of hydrogen. Okay, whenever you write per mole, you have to specify what that mole is, because there's 3 different substances here. It has to be per mole of what? Because it'll be different for different substances. Okay, so those are 2 ways of understanding what the energy is. It can be right in the equation, or it can be written beside it, and usually there's a bit of a gap. And then lastly, we can use a potential energy diagram. All right, so we had said potential energy diagrams have potential energy on the axis measured in kilojoules. Then we've got reaction progress on the bottom. Down here, the reactants. Okay, so if we think about this, this is an exothermic reaction, which means the products have to be lower than the reactants. Okay, because as the reaction goes on, energy is lost. So we'll say here, delta H equals negative 285 kilojoules. Again, it's not molar enthalpy, and we'll write the reaction out. So it was the formation of water. And we should have our states here, because the different states actually result in different energy changes. So that's a whole other topic that we'll look at later. So this is a potential energy diagram, and it can give you either from the axis the values themselves, or written on it what the enthalpy changes that you need for your calculations. Now, we said this in part A, the reverse of any reaction also reverses the enthalpy change. So splitting water into its elements, if the forward reaction was releasing energy, this is going to require 285 kilojoules per mole of hydrogen gas. Okay, and we can represent that the same 3 ways, but with the opposite sign now. So that wraps this up. There's lots of practice questions for this. It's a big concept in terms of energy and calorimetry, so be sure to practice. There's some textbook work, there's some worksheets with some answer keys, so whatever it takes, just play around with this and see the relationship between the variables and the scenario that's being studied. So I hope that helped, and good luck with the practice questions.